Hello, this is Anthony Schmitt for ME's 3708. I'm here to do video topic number 8, and what we're going to be talking about is fatigue failure. Now, fatigue failure is something that can lead to very catastrophic events in mechanical engineering and in life in general. So it's a very important topic. We want to make sure we know ways to prevent fatigue failure when we're designing as mechanical engineers, and what that takes is a deep understanding of fatigue. So that's what we're going to go through today. Well, let's begin. Now, the most dangerous thing that we can look at from fatigue is a crack, and when the crack happens from fatigue, usually more fracturing will happen if fatigue continues. So we have a couple of different kinds of fatigue. We have static and cycle fatigue. In the static fatigue, we have just this moment, this constant fatigue on this piece for this example, and there's a crack here, and then this moment will cause a crack to propagate and become much worse. Now, cycle fatigue is a little different. The moment here causes the stress will go back and forth and cause stress on both sides, and eventually stresses will meet and the crack will eventually fail. So two things we gotta consider in fatigue is the magnitude of the loading that causes fatigue, and also the cycle number of the loading, which we'll get into here. It has to do with this cycle fatigue. And our strategy for that, we're going to predict the fatigue depending on the loading and cycling number, and then ultimately prevent the fatigue from happening, and that's how we do it. Now, there's 3 stages to a crack when fatigue failure is happening. The first stage is a very small crack. We call it a micro crack, and this is due to cyclic plastic deformation. And when that begins to grow, we get into stage 2. The crack progresses. It repeatedly opens and closes, and it creates bands called beach marks. Stage 3, crack is propagated far enough that the remaining material is insufficient to carry the load, and then it fails. So we need to prevent it from getting to stage 3. We don't want it to get to even stage 1, but stage 3 is when it'll actually fail. It's important to note that cracks can increase stress, and the way we can analyze that is our stress concentration factor, which is K sub T. Now, the equation for this, sigma y max over sigma. Now, our equation for sigma y max is 1 plus 2 C over D, all multiplied by sigma. And so then we can just write our stress concentration factor as 1 plus 2 C over D. In addition to the stress concentration factor, there is the stress intensity factor, which we call capital K sub I. This is equal to sigma square root of pi A. Sigma is our nominal stress, which relates to our stress field equations, which I won't go into just yet. And then A is the length of the crack. A stress intensity modification factor can be incorporated in this equation. The modification factor is signified with beta, and so the equation becomes beta sigma square root of pi A. And the stress intensity modification factor is for various loads and geometric configurations that we might run into, and tables for beta are found in the book, and figures 525 to 530 present common configurations. Alright, so there's also the critical stress intensity factor, which we also call the fracture toughness. And this is when the crack propagation initiates failure. So this is that critical value when failure occurs. And we can use this to find the safety factor, and it's KIC over KI. This is the critical stress intensity factor over the stress intensity factor. So the next part is about analyzing crack growth, and we have this curve that we can look at to help us understand that. It's the curve of log of dA over dN and log of delta K. And what we end up is with these three regions. One is the initial cracking, one is the propagation of the cracking, and then unstable crack. And this is where we see our failure happen. One thing we can, a little detail here, if we increase the stress ratio R, this curve moves in this direction. And approximate the crack growth in region 2, which is the propagation of the cracking. We approximate the crack growth with the Paris equation, which is dA over dN equals C times delta K to the M power. And C and M are constants that we find in table 6.1. Furthermore, we can predict the cycle life NF with this equation. It's the integral of dN from 0 to NF equals 1 over C, integral A initial to A final, dA over beta delta sigma square root of pi A, all multiplied by M, our constant M. Our constant beta isn't always constant, and when it isn't constant, we can use this algorithm. It's delta n equals 1, then we have delta A sub j equals C times delta K1, M to J to M, delta n j, and then A sub j plus 1 equals A sub j plus delta A sub j. And this is until we reach a final, A sub f. So now what we'll get into is this idealized SN curve, our fatigue strength, and our number of cycles in the curve, and this is the ideal version. So it takes us from our ultimate tensile strength to our S sub E. We have two changes in the curve. One is at 10 to the third, one's at 10 to the sixth. And our curve can be quantified with SF equals A times N to the B. Now these constants A and B can also be stabilized in equations. So A equals F ultimate strength squared over S sub E, and B be negative 1/3 log F ultimate strength over S sub E. Now the S sub E mentioned previously is our endurance limit, and it's a real big long equation, just a bunch of different factors multiplied by each other. K sub A is our surface condition modification factor. K sub B is our size modification factor. K sub C is our load modification factor. K sub D is our temperature modification factor. K sub E is reliability factor. K sub F is a miscellaneous effects modification factor. Then our S sub E prime is called a rotary beam test specimen endurance limit, and this is prepared from a test specimen. We use all these to calculate our endurance limit, S sub E. Now, if we have a notch, we have to take a look at our notch sensitivity. And this is found from our concentration factor that we found previously. We have K sub F minus 1 over K sub T minus 1. And that is our dynamic and our static.